All right, so here's our second podcast of the unit talking about the basics of electron configuration. And this is just going to cover page 7. And we're not actually going to get into writing electron configurations, but we're going to get the basics of what it is so we understand what we're doing next class when we start writing them. So remember about the electron. Originally, or really one of the more modern ideas, was the Bohr model of the atom, where we had electrons on defined energy levels. And the thing that was wrong with that was that Bohr's model had all spherical orbitals. The quantum model of the atom, which Mr. Heisenberg helped us develop, which we also called the electron cloud model, figured out that orbitals are really just an area of probability where you're most likely to find an electron, and also very importantly for us, not all of those energy levels and sublevels, those orbitals, are spheres. There's some in some very weird shapes, and they get pretty weird, even weirder than what we see in this picture here. So the shapes that you need to know are S, P, D, and F. And you don't have to be able to draw them, but you do need to be able to recognize them. So if you don't want to try and draw these weird shapes here, what you do need to recognize is kind of the shapes of these orbitals. S are spherical shaped orbitals. There we go, that word came up. P are peanut-shaped orbitals. D I kind of think of as daisy-shaped orbitals, kind of starting to look kind of flower-like. And F kind of looks flower-like, but you'll see some of these orbitals, I'll show you some more different pictures of them, get a little bit freaky, but they're also kind of flower-shaped. So whatever word you can think of that reminds you of that F orbital letter. Now, each different shaped orbital might have multiple different orientations. I'm showing you a few different p orbitals, and there can be multiple orientations of the same shape on each energy level, and they actually overlap to form this kind of cloud-like shape. So we have what we call the px orbital is all oriented on the x-axis, the py orbital on the y-axis, then this vertical p. They're all peanut-shaped orbitals. They're all p orbitals, but they're oriented in different directions, and when they overlap, they make this kind of big cloud-like shape. And the important thing to recognize about these different orientations is that 2 electrons fit in each separate orbital, which means that inside each set of orbital, there is a maximum number of electrons on each energy level. And that's what I want us to go back. Underneath where you wrote sphere, peanut, daisy, and freaky or flower, I want to write down those number of different orientations. So S actually only has one orientation. On each energy level, there's only one sphere-shaped orbital. P, there are actually 3, like I just showed you. They overlap to that cloud-like shape. Then the daisy, the D orbital, has 5 orientations. You might see this pattern, 1, 3, 5. F has 7 different orientations. Like I said, some of those get a little bit freaky. Now, if we come back to that idea that there are 2 electrons that can fit in each of these orientations, that means that 2 total electrons will fit into sphere orbitals on each energy level. 3 orientations of p orbitals means that 6 total electrons can fit in their orbitals. D can fit a total of 10, and F can fit a total of 14. So I do need you to make sure you write down these different number of orientations and total electrons up underneath where you wrote down those shape names. Now, the last idea that I want to talk to you about is kind of building the atom and how all of this comes together in the actual electron configuration that we're going to be writing. So this is an example of scandium, and we're going to build scandium up from the basic level. And so you see here, this is the 1s orbital. So this is the first energy level, S-shaped, spherical shaped orbital coming in, centering around the nucleus. And then the next one to come in is the second level S-shaped orbital. Notice it's bigger. It's still spherical, but at a higher energy level, it's a larger sphere. Then on that second energy level, we can also add in some P-shaped orbitals. So we got that PX, PY, and PZ, all coming to overlap each other and those S-shaped orbitals. Then we've got the 3s that comes in, those 3 P's. Once again, there are 3 of them flying in. And then the 4s. And then we've got some D's. So the 3D. Remember, there's 5 different orientations of D's, so there's a lot of these here. But the key idea is they keep getting bigger as the energy level gets bigger, and they're all overlapping. So what we're going to be doing is labeling how many electrons are in each of these orbitals as we kind of build up the atom, a lot like what this video did. So here, electron configuration, as I've already kind of mentioned, it describes where all the electrons are located in the electron cloud. So if we write something like 1s2, 2s2, 2p1, that describes every single electron in its position, what energy level and shaped orbital they're in a boron atom. And as you can see, it's made up of a sequence of terms with 3 parts, like that 1s2 term. The big 1, actually, let's come back to the 1, because we recognize that letter there. The letter represents the orbital shape. The big 1, the large number, the coefficient in front of that letter, represents the energy level, how big of an orbital that is. And then the superscript number on that letter tells us the number of electrons in that orbital shape on that energy level. And in general, we're going to practice writing these together in class. The more electrons and orbitals that an atom has, the more of these terms the electron configuration will have. Just to compare, you can see fluorine, which is element number 9, has a much shorter configuration than scandium, that element we just saw built, that has 21 electrons. And you can only imagine how many gold would have down there at element number 79, or ogynthium at 118. So these can get pretty lengthy, but it's a pattern, and we're actually going to use the periodic table to help us put together this pattern. So that's where our podcast is done for the day.